Okay, question 14 asks us to find the critical points of f of x equals the ln of 2x cubed plus 3x squared minus 12x plus 1000, and we're told that we do not need to find the y values. As always, critical numbers come from the derivative, either the derivative being 0 or the derivative not existing. So I'm going to start by finding f prime. We got, well, actually before taking the derivative, I'm going to identify what type of derivative this is. This is a function f of x equals the ln of w. And when we take the derivative of f of w, or take the derivative of ln of w, we get w prime divided by w. That's our special rule for the derivative of natural log function. So for our particular w prime is going to be the derivative of 2x cubed, so 6x squared from the power rule, plus 6x, that's the derivative of 3x squared, minus 12, for the derivative of negative 12x, and then the derivative of 1000, because 1000 is constant, the derivative is 0. And then down below, 2x cubed plus 3x squared minus 12x plus 1000. Okay, and then there's not much to do to simplify this. I'm going to common factor a 6 from the top. And we have x squared plus x minus 2. On the bottom, I'll just copy it. So a quick comment to make is that inside this course, we're going to describe critical points or critical numbers that come not just from the derivative being 0, but also the derivative not existing. In this case, the derivative not existing would mean the denominator being equal to 0. The reason I'm not going to look at that, I'm not going to examine that, is because if the denominator is 0, then that would be an x value that would also make f of x equal to the ln of 0. Because everything inside the brackets of the original function, so that ln function, everything in the brackets is the denominator inside the derivative. And you cannot take the ln of 0. 0 is not in the domain of the ln of the log function. So there's no point in looking for where the denominator is 0. We only need to check for where the numerator is 0. So we have 0 equals 6 times x squared plus x minus 2 divided by 2x cubed. I'm just going to clean this up a little bit. 2x cubed plus 3x squared minus 12x plus 1000. I'm going to cross multiply by the denominator. And then on the numerator, the 6 times x squared minus x, or plus x minus 2, I'm going to quadratic factor that using a product and sum method. The mystery number is multiplied to give negative 2 and add to give positive 1. That combination will be plus 2 and minus 1. And multiply to give the negative 2, and they add to give the coefficient of 1 in front of the x in the middle. Okay, so on the left-hand side, we just have 0. 0 times all that stuff is 0. And now we have a product of 3 terms equals 0. The first term is 6. 6 is never 0, it's just 6. The second term is x plus 2. X plus 2 is equal to 0 if x is equal to minus 2. And the third term, the bracket x minus 1, that term is equal to 0 if x is equal to 1. So those are the two critical numbers. Okay, question 15. Instead of starting with f of x and having to take the derivative, it gives us f prime of x. So the derivative is already done. We're asked the same question, determine the critical numbers. So I'm going to set f prime of x equal to 0. So we have 0 equals 3 times x minus 1 squared. Now x squared minus 4, that factors. That factors into two terms. X minus 2 times x plus 2, it's a difference of squares. So I'll factor it. And then the x squared plus 9 does not factor. Okay, now I'm going to set each of these terms equal to 0. I guess I'll mention the 3. 3 is never 0, just always 3. X minus 1 all squared, that's 0 of x is equal to 1. X minus 2, that's equal to 0 of x is 2. X plus 2, that bracket's equal to 0 of x is negative 2. And then there's no solution from the last one because x squared plus 9 is never 0. So a little comment to add is that x squared plus something, x squared plus 9 is not equal to 0 for any x. X squared plus 1 is not equal to 0 for any x. X squared plus 7 is not equal to 0 for any x. X squared plus k is not equal to 0 for any positive k value. So if k is greater than 0, x squared plus k will never, ever, ever be 0. And you can picture that if you want. You can either come to terms with that through algebra. X squared is always positive, and if k is positive, you're taking something positive and adding a positive number to it, and you can't possibly get 0 from that. Or you can think about it in terms of the graph of what quadratic a parabola would look like. X squared plus k looks like this. So k would be that y value there. And then the line y equals 0, when we're setting a parabola equal to 0, we're looking for what is that parabola across this line. So a parabola of this form will never cross that line. It's above the line. Whereas when we have two solutions, that would be take that purple curve and pull it down. That would be where the parabola crosses twice. Okay, so anyways, for this problem, we have these three solutions. 1, 2, and minus 2. All right. Word problems. So this topic is still the same topic as the previous questions. It's still finding max and finding min. In your previous calculus course, you likely did optimization questions of a very small number of types. One of the most common types of optimization problems is this one, a problem where you have a farmer who wants to build a fence, and this farmer only has so much fencing, and the question is almost always to determine the geometry of the fence that would maximize the area enclosed. And sometimes there's restrictions, like we're going to build the fence along a river, so you don't need fence along all four sides, or maybe you want double fencing along one side. There's all types of different formulations of this question. And in this version that's here, there's two different varieties. So in part A, this character, this Waldo guy, wants to use double fencing along the sides of the fence that run perpendicular to the river. So I'm going to draw a picture. Waldo has 480 meters of fencing, wants to build a rectangular fence against the river. So I'm going to draw a river. I'm going to draw the fencing. So this is the picture of what we're trying to draw, or a picture of what we're trying to accomplish. We want to find, in question A and in question B, how would we maximize the area enclosed if we're limited to using 480 meters of fencing. Now, for part A, Waldo wants to use double fencing along the sides that run perpendicular to the river. So perpendicular means at 90 degrees to the river. So from this picture, that would be this side and this side. And if you draw your picture rotated, then your double sides will be rotated too. I'm going to label this diagram. I'm going to call this distance from here to here, I'm going to call that x. This distance, actually, we'll just add extra lines there. It's already confusing enough. Just call that x. This distance going up and down, I'll call y. And because this is a rectangular fence, the bottom is also going to be x. Question asks, what expression represents the one variable function that Waldo should maximize to max the area enclosed? All right, so let's think about area. Area is length times width for a rectangle. Based on the labeling that's here, that would be x times y. So we could say a of x comma y is x times y. The question wants us to find a one variable function. This is a two variable function. So what we need to do is we need to relate x to y. We define a relationship between them. And the way we're going to do that is we're going to use the 480. 480 fencing available means total fence sides equals 480. So built into that statement is the idea that if we want to maximize the area enclosed, we want to use all of the fencing. We don't want to use 470 meters and just leave a pile of 10 meters of fencing off somewhere. That's not going to give us the max. We're going to maximize by using all of our resources. So we're going to have 480 equals the sum of all the segments of fencing. On the top, we have an x component and another x component because it's double fencing. And up and down, we have one y component. And at the bottom, we have two x components. So I'll label this top, bottom, side. And on the left-hand side, we don't have any fencing because we're using the river as free fencing. So I'm going to clean this up. We have x plus x plus x plus x, so there's four of those, 4x plus y. We can then isolate for y. Y is equal to 480 minus 4x. That relationship between x and y is something we can sub into our two variable function. A of x comma y becomes a of just x if we replace the y with 480 minus 4x. So x times 480 minus 4x. I'm going to do some highlighting in a second. Okay. And let me just double check what question A is asking for. That's the one variable function. I'm going to simplify it a little bit. I'll multiply the x to the bracket, 480x minus 4x squared. So if we find the maximum of that function, And that will tell us the ideal dimensions to use to maximize our area enclosed. Okay, part B. Waldo wants to use triple fencing along the side that runs parallel to the river. Okay, so this needs a new picture. There's the river. I'm going to draw my rectangular fence. Even X, even X. Now we need triple fencing along this side. So 1, 2, 3. Okay, our area is still length times width. Is equal to x times y. So our two variable function, a of x comma y, is still x, y. We need to relate x to y, so 480 is equal to total fencing used. So 480 is equal to x plus y plus y plus y plus x. Let's label those. So we have the top, we have the bottom, and we have the triple layer side. So 480 is equal to 2x plus 3y. I'm going to rearrange to get y by itself. So 3y is equal to 480 minus 2x. So y is equal to 1/3 of 480 minus 2x. Which is 160 minus 2 over 3x. We can then take our area function of two variables and make it an area function of one variable. So a of x is equal to x times y, so x times 160 minus 2 over 3x. And then I'll multiply that x to the bracket, 160x minus 2 over 3 x squared. Okay, then part C wants us to do the optimization, perform the maximization procedure for parts A and B, and find the optimum dimensions of the fence. So for a of x is equal to 480, I'm getting ahead of myself, 480x minus 4x squared. We'll take the derivative, set it equal to 0, so 480 minus 8x. So 8x is equal to 480, x is equal to 480 divided by 8, which is 60. And we can find y. (480 minus 4x). So 480 minus 4 times 60, we get 240. So for this part, thus max if x equals 60, y is equal to 240. And then for the other one, and for a of x equals 160x minus 2 over 3x squared, we're going to set the derivative to 0. 4 over 3x, 160 minus 4 over 3x is equal to 0. So 4 over 3x equals 160. I'm going to divide by 4. 160 divided by 4 is 40. And then multiply by 3, 120. And then go back and find y. So y is 160 minus 2 over 3x. So 160 minus 120 divided by 3 is 40. 40 times 2 is 80. 160 minus 80 is 80. And we can conclude for this one, thus max if x equals 120 and y is equal to 80. So changing that, changing the thickness of different parts of the fencing makes a really big difference in terms of what the optimum dimensions are. So these are perhaps twists on the more traditional fence question you face in your high school course. Maybe just 3 sides and no double fencing or no triple fencing. Okay, last example. Big, scary looking paragraph, but the math itself is going to be more straightforward than the previous stuff. The tastiness of cake frosting is modeled by some random person with a recipe blog by the function t for tastiness, equals x times y squared, where x is the number of cups of butter in the frosting and y is the number of cups of sugar in the frosting. There are no other ingredients in the frosting. You plan to make a very large cake that will require 9 total cups of frosting ingredients. How many cups of sugar, how many cups of butter should you use to maximize the tastiness of the frosting? So I'm going to first draw an analogy to the previous question to say that our tastiness function has 2 variables in it. And we want a tastiness function of just the x variable only, 1 variable. So we need to relate y to x. And fortunately, we can do that because total cups of frosting is 9. So that tells us that 9 is equal to the total number of cups of butter plus the total number of cups of sugar. So 9 is equal to x plus y. That means y is equal to 9 minus x. So our function of 2 variables becomes a function of 1 variable. T of x is equal to x times 9 minus x all squared. Now this is not the easiest way to do the question. We can proceed like this, but it's actually easier. I'm gonna erase this. It's not wrong. This is fine. I'm going to erase this and show you, based on the precise format of the function here, x times y squared. It's better to isolate for x. I'll have an easier problem. So x is equal to 9 minus y. I'm just going to get rid of this. I'm going to clean this up a little bit. We need to relate x to y, so we can have a 1 variable function. X is equal to 9 minus y, so t of x comma y becomes a function of just t of y. So instead of x times y squared, we'll have 9 minus y times y squared, which is 9y squared minus y cubed. Okay, so I'll take the derivative, t prime of y, of 18y minus 3y squared. We're going to set the derivative to 0. So 0 is equal to, and common factor, on a common factor of 3 and a y out, we'll have 6 minus y. And this gives us 2 solutions. One solution is y is equal to 0. The other solution is y is equal to 6. Okay, next step, we want to get the x quantity. So I'm going to use the fact that x is equal to 9 minus y to do that. If y is 0, then x is equal to 9 minus 0, which is 9. And if x is 6, the y is 6, then x is going to be 9 minus 6, which is 3. So we get two critical points. (9, 0) and 3, 6. To check which one's the max, we could either check the concavity or we could check the output of the function. So if we check the concavity, t double prime of y will have 18 minus 6y. Take the derivative of t prime. And then I'm going to evaluate that at each of the two solutions at 0. So I'm plugging in the y value here. We get 18, which is positive. It means it's a minimum. Because positive means concave up, and concave up has this shape of a local minimum. And if I plug in the other y value, 6, I get 18 minus 6 times 6. So 18 minus 36, which is negative. Negative means concave down, which is a max. So based on the concavity analysis, we would say that 3, 6 is the maximum. We could also check t of x, y. So t at 9, 0, if we plug that critical point back into the tastiness function, we get 9 times 0 squared, which is 0. So a tastiness of 0. Now if we plug in the other critical point, 3, 6, we get 3 times 6 squared, which is definitely not 0. 3 times 36, which is 108, I think. So that's the max. That's the min. This would be a global max and global min analysis. Anyways, I think that's it.